Hello everyone, I am Manu Ramesh from the VADL lab at Purdue University, and I'll now be presenting our work Black Mirror Light Probe cow model for specular highlight removal to improve Holstein cattle identification. Holstein is a breed of cattle popular in the dairy industry. They are characterized by their black and white coat patterns. Visual identification means to identify these cows using images or videos from RGB cameras. On the slide, you will see an example of an identification system identifying a Holstein cow using key points. Visual cattle identification serves as the foundation for many cattle visual analytics tasks such as weight estimation, video retrieval, intake, attendance and behavior monitoring, and lameness detection. This is because any of these measured metrics must be tagged with a cow identity. This means that errors in identification propagate and affect all the downstream tasks. One such source of errors is specular highlights. The identification systems rely on memorizing the black and white coat patterns on these Holstein cows. These black and white regions must be correctly identified to recognize cows without errors. Black and white separation is through brightness and not hue because these colors are achromatic. Specular highlights on the black regions, such as these, make them appear white. This leads to the incorrect separation of the black and white regions, and it confuses the identification system, and this leads to misidentification. So, we must nullify the effect of specular highlights. For this, we observe, model, and invert scene illumination. Here, we list the characteristics of challenging scene illumination and the operational limitation. Firstly, the scene can be lit by multiple illuminants, leading to spatially non-uniform illumination both in hue and brightness. On the slide is an example image where the right side has a predominantly blue hue while the bottom left region has a reddish-orange hue. In the bottom left, you can also observe the specular reflection of the orange lamp directly above it. The illumination can also be temporarily non-uniform if the lamps of the dairy are changed to ones with a different hue. Finally, we are limited to work with pre-recorded data. This means that we cannot a posteriori measure light using physical light measuring instruments. So we need methods to color correct the scene. Available methods for color correction include both traditional and recent methods, both of which do not solve our problem. The traditional methods use statistical lighting models, which need less compute and are comparatively faster. The recent methods use neural network models that need more compute and are slower for real-time applications. The traditional methods compute and use statistics directly from the image that needs to be color corrected. The recent methods use knowledge derived from training datasets to color correct a given image. Examples of both types of methods are shown on this slide. We now present our method, Black Mirror Light Probe cow model, that aims to improve the performance of the downstream task and not to create a perceptually pleasing image. We discuss how this method works now. We first model a black cow as a black mirror and then observe it as it moves around in the scene and accumulate its reflections into a scene illumination map. The illumination map is then extended to cover the unseen regions, which are the regions where the cow has not walked in the scene wherever necessary. We then use the illumination map to color correct other cows in the same scene. To model a black cow as a black mirror, we use the dichromatic reflection model. Its equation is shown on the slide. It models the reflection as the sum of matte and specular reflections. Here, the S terms are the scale factors that depend on the object geometry. Rm and Rs are the reflectances with respect to matte and specular reflections. Li is the illuminant. We simplified the dichromatic reflection model by applying the following conditions. Firstly, we modeled the probe cow to be completely black and mirror-like. This makes the matte reflectance 0 and the specular reflectance 1. Next, we model the camera to implement scaled orthographic projection. The directions of the object surface normal, illumination, and the camera are all parallel. This makes the scale terms equal to 1. This gives us our simplified model for black mirrors. For each pixel location xy and I in RGB, we have IIXY equal to LIXY. In other words, the sample reflection map is the scene illumination map. Next, we observe the cow as it moves around in the scene and accumulate the reflections into a scene illumination map. The black cow paints the illumination map just like a brush painting on a canvas. Here we have the seen and the unseen region. The seen region is where the probe cow has been seen while computing the illumination map. There is a possibility for other cows to appear in the unseen region. Now this image with the black background is our computed scene illumination map. We now extend this map to cover the unseen region where other cows can appear. This extension is done using normalized convolution with a Gaussian kernel. This extended illumination map is now shown on the slide with a marked extended region. This extended illumination map is then used to color correct other cows in the same scene. To color correct an image, we consider each point in the illumination map to be the measured black point at that location and then apply the well-known black point correction algorithm given by the equation on the slide. Black point correction offsets the pixels by the black point value and then rescales it to fit the entire allowed range of 0 to 1. A cattle identification system could then convert the image to grayscale and threshold the pixels with a low threshold to separate the black and white regions. Now we discuss how we evaluate the different color correction methods. For this, we apply the methods to the task of cattle identification. For this, we first select a cattle identification system, plug the different color correction methods into this system, and then observe if the identification accuracy improves. For this purpose, we use the eidetic cattle recognition system, whose working is shown by the diagram on the slide. Given an image of the cow with top view, this system first localizes the cow instance using key points and instance mask, and then converts it into a canonical pose. The instance in canonical pose is then pixelated and binarized to obtain a cow barcode. This barcode is then matched to its nearest neighbor in the set of training barcodes called the catalog to get the predicted identity. In this flow, we introduce a block that color corrects the video frame before the identification system processes the instance. This color correction block is where we plug in the different color correction methods that include the traditional, recent, and our black mirror light probe cow method. We now discuss the dataset and evaluation metric that help us evaluate the color correction methods. The dataset has video clips, each with only one cow walking along a short path. These clips were recorded from 2 days of summer 2022. The video clips from the first day are used to train the identification system. These are of 153 cows. The video clips from the second day are used for evaluating the identification system. These have 148 cows. Example images from these clips are shown on the slide. The evaluation metric that we use is the number of correct identifications, which is the total number of cow instances that are correctly identified in all frames of all the evaluation video clips. Now we present our results. First, we have the quantitative results. The baseline result is from the identification system without any color correction. The traditional methods are highlighted in purple, and the recent methods that use neural network models are highlighted in blue. Applying our color correction method results in the number of correct identifications improving by 7%, and our method performs the best here. Now we have the qualitative results. This slide shows 3 example cows. Sample images of the cows are shown in the leftmost column, and the barcodes generated after the application of the selected color correction methods are shown in the other columns. In the first row, only hours and the IID method generate the correct barcode, which is a completely black barcode for the completely black cow. In the second row, only hour method identifies the two white patches on the bottom of the cow while correctly negating all specular highlights. In the third row too, only hour method correctly identifies the top white spot while also identifying the bottom white patch as a single connected component. Finally, our method, black mirror light probes, is fast for inference because it does not use any neural network models, nor does it compute image statistics at the time of inference. This makes it suitable for real-time applications. Further, it is accurate and adaptive. This is because it directly models the ground truth lighting information at the pixel level and uses objects that are already present in the scene to measure the scene illumination. And it is designed to improve the performance of the downstream task and not intended to create perceptually pleasing images. Our method has a limitation, that is, it has limited ability to color correct the unprobed areas. However, extending probe regions using normalized convolution is proposed as a workaround. Future work could include developing non-flat cow models to handle strong directional lighting. Here are our key references. Thank you.